Remember, these redshifts are determined with that color technique, where the filter, you remember that slide where the images drop out and so forth. It is an approximate method, and it has been known to be wrong. And so getting the spectrum of the galaxy in order to measure the redshift accurately is the next step. And the first results are very promising, and I've decided to show the object that we found with Hubble that we thought was at 11.9, but we weren't sure. And Emma Curtis Lake, who's an astronomer at the University of Hertfordshire, managed to get this spectrum. And here's that hydrogen absorption. There's no question. It's at a redshift of 11.6, so we're very pleased about that. And here's another spectrum, so where we can see the fingerprints of nitrogen, helium, carbon, magnesium, oxygen, neon, in a galaxy at a redshift of 10.6 or so. So this is the beginning of chemistry, which we couldn't do with Hubble at all. So, you know, the logical step now, to go back to this decline, is we would expect the chemical composition of these objects to be going down because the stars have had less time to synthesize the heavy elements that we see today. And so, you know, the logical thing would be to find an object that's chemically pristine, and that would be the first telltale indication that we finally reached the beginning of the story. So I'm more or less done. You know, this key signature is going to be the telltale signature that we don't see the heavy elements that we see around us today in these early galaxies.